every photo you've ever taken, every song you've ever streamed, every word in every email you've ever sent, every video game, every bank transaction, every text message, every YouTube video. All of it, at its most fundamental level, is nothing but a very long string of zeros and ones. Why? Out of all the possible ways to represent information, why did the most advanced civilization in human history choose the most primitive number system imaginable? The answer involves a 17th-century philosopher, a Chinese divination text that is thousands of years old, and the physics of electricity. And it will completely change how you think about every device you own. In 1679, a German mathematician and philosopher named Gottfried Wilhelm Leibniz published a paper describing a mathematical system built entirely on two digits, 0 and 1. He called it the binary numeral system. He believed it was the purest possible expression of mathematics, creation represented by 1, nothingness represented by 0. He was deeply religious, and he saw in binary a mathematical reflection of God's act of creating something from nothing. What happened next is one of the stranger coincidences in intellectual history. A Jesuit missionary brought Leibniz a copy of the Ching, the ancient Chinese book of changes, a divination text at least 3,000 years old. The Ching uses 64 hexagrams, symbols made of combinations of solid and broken lines. Solid line, yang. Broken line, yin. 6 lines per hexagram. 2 states, 6 positions, 64 total combinations. Leibniz immediately recognized what he was looking at. The I Ching was a binary system. The ancient Chinese sages had independently developed binary combinatorics millennia before Leibniz was born, for purposes that had nothing to do with mathematics. The same fundamental pattern, 2 states, combined in sequences, had emerged in 2 completely separate cultures, on opposite ends of the world, thousands of years apart. Binary was not invented. It was discovered, because it reflects something true about information itself. Leibniz's binary mathematics remained largely a philosophical curiosity for 200 years. Then electricity changed everything. When engineers in the early 20th century began building the first electronic computers, using vacuum tubes, relay switches, and early circuit components, they faced a fundamental design choice. How do you represent information in an electrical circuit? You could try to represent numbers directly as voltage levels. Store the number 7 as 7 volts, the number 3 as 3 volts, and so on. Early analog computers tried this approach. The problem is that electrical circuits are noisy. Voltage fluctuates. Components drift. A circuit trying to distinguish between 6.8 volts and 7.2 volts will make mistakes. And in computation, mistakes compound into catastrophic errors. Binary solves this problem elegantly. Instead of distinguishing between 10 or 20 different voltage levels, binary only needs to distinguish between 2 states, high voltage and low voltage, current flowing or not flowing, switch open or closed, on or off. These 2 states are so dramatically different from each other that a circuit can distinguish between them with enormous reliability, even in the presence of significant electrical noise. A transistor, the fundamental building block of every modern computer, is essentially just a switch. It has 2 stable states, conducting, 1, and non-conducting, 0. That's it. And from those 2 states, combined in sequences of billions of transistors switching billions of times per second, every form of information can be encoded and processed. Text works through encoding systems like ASCII or Unicode, which assign a binary number to every letter, number, punctuation mark, and symbol. The capital letter A is 01000001 in binary. The space between 2 words is 00100000. Every word you're reading right now was, at some point in its journey to your screen, stored and transmitted as a sequence of zeros and ones. Sound is captured by measuring the amplitude of an audio wave thousands of times per second, 44,100 samples per second for CD quality audio. Each measurement is converted to a binary number. When playback happens, those numbers are converted back to electrical signals that move a speaker cone. Your favorite song is, fundamentally, a list of billions of numbers. Images work similarly. Every pixel in a digital photograph has a color, and every color is defined by the intensity of its red, green, and blue components, each stored as a binary number between 0 and 255. A single megapixel image contains 1 million pixels. Each pixel requires 3 8-bit binary numbers. That's 24 million individual bits, zeros and ones, for 1 megapixel of image data. The entire digital world is built on this foundation. Not because it's poetic or philosophical, or because engineers like the number 0, but because the physics of electricity, at the most fundamental level, is binary. And Leibniz saw that truth 300 years before anyone had a circuit to prove it. The next time you take a photo or send a message or stream a song, somewhere inside the device in your hand, billions of tiny switches are flipping between on and off billions of times per second. Each switch knows only one thing. Is current flowing or not? 1 or 0? And from that unimaginably simple question, asked unimaginably many times, comes everything. Every image, every word, every song. Every idea that has ever been stored or transmitted digitally. All of human knowledge, encoded in the simplest possible language. Yes or no, on or off, 1 or 0. Leibniz would have found this profoundly beautiful. He wasn't wrong.